Alright, let's talk about some of the in-betweener stuff. This is somewhat still wave characteristics, but we're not going too deep. We're going to be covering in this video topics on phase interference and standing waves. So, this is kind of a math recap. If you haven't learned this yet in math, not a big deal. It is helpful to think about it in terms of the way the math lays it out. And so I've got this wave. It's one complete wave, 12-meter long wavelength with a 4-meter height amplitude. And we want to know which positions would we indicate the following degrees. So what would we say is 0 degree, 90 degree, 180, 270, and 360? Well, if you remember in math, 360 degrees is one entire revolution, or one complete circle. So really what I'm asking you down here is, where do we begin? Where are we a quarter of a revolution through? That's 90. Where are we one complete revolution? That's 180, or one half a revolution. That's 180 degrees. Where are we three quarters of that revolution? 270 degrees. And then when are we back to where we began, or 360 degrees? Remember, this is both 0 and 360 degrees. So if we look at this wave in the very beginning, well, that's where we started. So that's 0 degrees. Okay? Then, as we already said, one entire revolution later, or one whole wavelength, that's also 0 degrees, or 360 degrees, whatever helps. So I'm going to label this spot 360. Label this spot 0 degrees. Now, as we see in the circle, a quarter of a revolution is 90, then a half revolution is 180. So, quarter of a revolution, that's at my crest up here, it's 90 degrees. So I would go ahead and call this 90 degrees. Half a revolution, that's where I'm back at the equilibrium here, so that's 180 degrees. Three quarters of a revolution. Here's my 270 degree mark. And like I said, back in the beginning, 360 degrees. This isn't going to come up too often in introductory physics or Regents physics, high school physics, but it would come up in some of the college level classes like AP or college level physics. And it's easier overall to just think it through this way anyhow. So keep this stuff in mind as we continue. Let's talk about phase. I've got myself a periodic wave here with a bunch of different points labeled. And we have two terms that we need to talk about. We have in phase and then out of phase. And another way of thinking about it is completely in phase and completely out of phase. Everywhere in between would be partially in phase or partially out of phase. Anything in phase is 0 degree difference, or 360 degree distance, or complete wavelengths apart. One wavelength, two wavelengths, three wavelengths apart. I don't care if it's 10 wavelengths apart. Those parts are all in phase with each other. And then, opposite of that, out of phase, would be half a wavelengths apart, or 1.5 wavelengths apart, or 2.5 wavelengths apart, or every 180 degrees. This is important because when we get into how waves interfere with each other, you'll understand sometimes we want them to be in phase, and sometimes we want out of phase or somewhere in between. So let's take a look at this diagram. I'm going to label several points that are in phase with each other. Well, let's look at A. What is in phase with A? Well, in phase would be every whole wavelength, or every 360 degrees. So we've got 90, 180, 270, 360. Okay, E is in phase with A. I is in phase with A. I is in phase with E. Continuing, M. M is in phase with A. All of these that are circled in green are in phase with each other. So M is in phase with I, M is in phase with E, E is in phase with I, all of them with A. They're all in phase with each other. I could continue up on the crests. B, F, J, and N are all in phase with each other. They're all whole wavelengths apart. Or I can do the same thing on my troughs. D, H, L, they are all in phase with each other. Heck, we can even look at these equilibrium spots. C is in phase with G, which is in phase with K, which is in phase with O. Now, I'm going to go ahead and erase all that, talk about what's out of phase, but all the light color are in phase with each other. So what's out of phase with A? Well, that would be every half a wavelength away. So A is out of phase with C, half a wavelength apart. C is also out of phase with E, also half a wavelength apart. But E is not out of phase with A. They're in phase with each other because they're a whole wavelength apart. So it's got to be halves. We got a ton up here. We can pick any of them. For example, what's out of phase with F? Well, H is out of phase. J is in phase. L is out of phase. Half wavelength. 1.5 wavelengths. D is out of phase. These are all out of phase with F. Not each other, but with F. They're out of phase with F. Half a wavelength away, half a wavelength away. Out of phase. And then we get things like partially out of phase or partially in phase. Like B is partially out of phase with C. Not 180 degrees apart, but definitely not 0 degrees apart, somewhere in between. These are just points on a single wave. We can also have entire waves that are in phase or out of phase. For example, I'm going to draw a red wave right on top of the black one here just so I can manipulate it. That red wave is in phase with the black wave. It is right on top of it. Let me lock this black wave in place if I'm allowed to here. There we go. But that red wave can also, connect these two, can also be 100 or 360 degrees away. So this is still in phase with the original black wave. It just started an entire wavelength later, or sooner, however you want to look at it. Also in phase. Okay? Out of phase means it's 180 degrees offset. So my crest of one needs to line up with the trough of the other. Here, we are out of phase. In phase. Out of phase. In phase. And then we can be somewhere in between, so partially out of phase. We could use words that'll say 90 degrees out of phase, which means the crest of one will exist 90 degrees later, or at this intersection point. Just understand that terminology. In phase, they're in line, whole wavelengths apart. Completely out of phase, half wavelengths apart. Somewhere in between is somewhere in between. Phase. It's going to come into play when we talk about this next stuff. So let's first define two things. We got two different things going on with the left and the right. We're talking about wave reflection. What do waves do when they hit a boundary? So when a pulse or a wave, now this picture is showing a pulse, but it's the same thing for a wave. When it reaches a fixed boundary, something that won't move, such as it being tied down to this pole. When it hits that boundary, it will completely invert and then reflect back. So you see the incident wave, and then it inverts and reflects back. Very important to understand. Everything else about the wave stays the same. The speed, the wavelength, all of it stays the same. It's just inverted and then going the other direction. That's different than when it hits a non-fixed boundary. If you look over here, you'll see that wave is allowed to move. Maybe this is a ring on a pole. Turns out that when the pulse or wave hits that non-fixed position, it will still reflect back, but this time it maintains the same side, so it will not invert. It'll stay positive or it'll stay negative. It really depends on its original incident as it hit the boundary. This is important because when we talk about this next concept, interference, you really got to understand why waves might end up interfering. Let's first define it. Interference is the effect produced by two waves passing simultaneously through a region. Superposition. When waves overlap, the resulting displacement is the algebraic sum of the individual displacements of each wave. What is this? This is fancy talk. Interference basically means what happens when two waves exist on each other, and superposition is basically the name for the overall result. So let me show you this. We've got identical pulses up here. I've got this oscillating system. It's going to oscillate once or twice, depending on how many times I hit it. That's going to send a pulse down this rope. I'm going to first show you fixed reflection. So the pulse goes down. It's fixed, so think about what should happen. And there we go. Now, while the next one is heading back to the left, I have a new pulse to the right. And my question is, what happens when these pulses get on top of each other? Now, think about this. Remember, pulse, waves, it's just energy traveling through the medium. It's not the medium moving itself. It's energy traveling through the medium. So my question is, what happens when this energy is on top of more energy? When this positive amplitude is on top of this negative amplitude? Will it ignore? Will it just pretend it's not there? Will it completely cancel out and nothing will happen afterwards? Will it bounce off of each other? Will it pass through each other? These are all random questions, but there's only one answer. And I'm going to show you it once, and then I'm going to clarify what you see, just in case you see it wrong. So I'm stepping forward. Here they're completely on top of each other. And if they continue to exist, as I step forward more, you'll see them re-exist. Let's see what happens. And sure enough, they go right and they continue. And so I'm going to rewind and I'm going to explain to you what you really are seeing here, just in case you're seeing it wrong. Because there's two really types of scenarios that are happening here. Either they are hitting each other and then bouncing off of each other, or they're hitting each other and passing through each other. If they were matter, if they were basketballs, for example, they'd hit each other and bounce off of each other. But it's not matter, it's energy. Really what's happening is they're just passing right through each other. This pulse that you're seeing here was the pulse that we saw on top to the left. So let me go back. There. Now I'm going to draw this one red so I can move it and emphasize this. I'm going to draw this one blue. Unfortunately, the blue and the red won't move once I continue to inch more forward, but I'm doing this for a reason. So at this spot in time, it's when the red was completely on top of the blue, and they're temporarily canceling each other out. If I had a meter here measuring the energy, it would measure nothing. But then I'm going to let them keep going forward, and my question too is this guy here the red one or the blue one? Turns out, because it's energy, it just passed right through. It's still the red one. This one's still the blue one. They both continue as if there was nothing there. Or if you can think about energy as a little dude or a little dudette, they are not interacting with each other at all. They don't know they exist. They simply just pass right through each other. But when they're on top of each other, they are canceling out. This is known as destruction, destructive interference. It's a little easier to see if we have different size waves. So that's what I'm going to show you. Two different pulses. And I'm going to watch this in real time so we can just visually see what's happening here. Goes down. It's still fixed, so it's going to hit. It's going to reflect back. And then I have a different wave. And you'll see, and it doesn't... All right, let me pause that. Remember, the little one is up top. The big one's on the bottom. You see here how we didn't actually completely destroy? There's still a little bit of something left. You get all kinds of weird patterns that can exist from this. Let's try it again. Passes right through. This one's a lot easier to tell, because you'll see that long pulse down the bottom still always there. Can you picture it? But this bottom part that was here is getting canceled out by this part that is here. What happens when the ends are free? Well, when the ends are free, if you recall, the pulses... Actually, let me make them both identical pulses. The pulses, well, we're trying to think about it. The free end, is it going to invert or is it going to stay on the same side? Yeah, you're right. It stays on the same side. Now, when they're on top of each other, what's going to happen? Are they going to completely cancel again? Are they going to just pass right through each other as if they weren't there whatsoever? Or are they going to add up let's see. Look at that, it turns out they add up. This is known as constructive interference. They add together. So if they were both a value of, say, positive 1, then they end up staying a value of positive 1. Pretty neat stuff. But when they're on top of each other, they're positive 1 plus positive 1, making 2. So that's an amplitude of 2. All right, let's move on. Let's take a look at it and break it down one by one. So constructive interference is where the amplitudes are on the same side. So either two positive amplitudes, two crests, or two negative amplitudes, two troughs. As long as they're on the same side, they're going to construct or they're going to add together. So in this example, I've got a 1 and a 1 creating a 2, or a 2 and a 2 creating a 4. It doesn't really matter. But if you notice down here, so the first scenario, these two pulses are approaching each other. Second area here, they're now constructively interfering. Now down here, they're going to continue back in their merry way. So once again, this pulse right here is this pulse right here. They're the same pulse. And this pulse right here is this pulse right here. And this purple one that I'm going to draw in the middle is the sum of the two. Destructive is the opposite. They're going to cancel each other out. So if I have positive 1 here, I have to have a negative amplitude. And if they're the same value, they're going to completely destroy. So again, if this is, I'll make this one red. If this is my red pulse here, as it continues after the destruction, it's my red pulse here. And if this is my green pulse here, or green, my blue pulse there, here's my blue pulse here. And in this middle area, once again, they're completely destroying. And you can see that pretty well from this little graphic right here. All right, and let's just do one brief example of somewhere in between. This is what we'll call partial destruction, where they're not going to completely cancel each other out. So let's think about it. What would happen when A is on X and B is also on point X? What would the resulting amplitude look like? Well, we've got a positive 2 amplitude, a negative 1 amplitude. We should have an overall positive 1 left over. You'll get, and it's going to be a little bit difficult for me to draw, but you're going to get something that looks like this when B is on top of A. All right, and the last thing I want to talk about in this video is this concept of a standing wave. This concept won't completely disappear. It's going to come back into play when we discuss things like resonance and sound. It's a pretty awesome topic. I highly encourage you to check out YouTube clips on standing waves. Type in standing wave pattern, standing waves, standing wave effect. You'll see all kinds of neat stuff. Let's define it real quick. A standing wave is a wave produced when two waves of the same frequency and amplitude traveling in opposite directions in the same medium. Say what? Let's read this one more time. Let's make sure we get this. It's a wave that comes from the result of basically two waves, but those waves must have the same frequency, they have to have the same amplitude, but they must be going in opposite directions. You can see what this looks like in slow-mo down here. You've got this green wave to the right, and you got this red wave traveling to the left. They both are identical waves. The only thing different is the direction of motion. And the black wave is the wave that's being created from the interference pattern of the two waves on top of each other. So you can see if I try to pause this and break this down, try to catch it where, there. So when this red is on top of the green, you get constructive interference. You get this really high peak, this really low valley. And if I were to continue it and try to catch it when they're completely up, well, I didn't quite get it. It's going to be hard to trigger it. I'll try one more time. Right there. Oh, I nailed it. I'm proud of myself right now. Anyhow, when the crest is on top of the trough, you're getting complete canceling effect. You get destructive interference. And so you're going from these maximum areas of positive constructive interference to canceling destructive interference, and then in between. Well, if this happens over and over and over and over again, you get this ensuing black wave behind it called a standing wave. And if you think about it, if you do this really, really fast over and over and over and over again, if I would increase the speed to a much higher value, you would almost see a wave that's standing still. You'll see something like the design drawn to my left here. You'll see this thing right here. And you'll see a wave that seems to be existing in two spaces at once. when I am talking about this in class, I almost say take your hand and wave it in front of you really, 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 really fast. It almost looks like your hand is taking up more space than it does, and it's because it's going so quickly. When in reality, you know that it's either on the left or the right side. You know it's not actually both left and right, but if you go quickly enough, you're tricking yourself into thinking it's in two places at once. And that's really what a standing wave is. It appears that there's a wave above and below here, but it's not. It's just happening so fast that you get this great little pattern here. And this is known as a standing wave pattern. And there's a few things that you definitely need to identify for now. It's going to come into play later on. You have your antinodes. These are the areas where you've got your maximum separation between your crest and your trough. This is where you're getting your construction. And then you've got your nodes, and these are the spots that appear that there's no energy at all times. These are going to be where you always have destructive interference. So the spots that I'm circling in green are my nodes. So in this particular standing wave here, I have 4 nodes. And then your antinodes are the areas of maximum displacement. And there are 3 antinodes in this standing wave. This does come into play later on. This is a very powerful effect. For now, just get the characteristics and it will be addressed later. Thank you.